Good morning. Let us discuss about the stresses induced on an oblique plane due to biaxial stresses accompanied by shear stress. Okay, consider this figure which is subjected to biaxial stresses sigma x and sigma y along with shear stress tau xy, and this tau xy which is acting on vertical faces will be accompanied by this complementary shear on horizontal faces also for equilibrium. Okay, so you'll have these shear stresses on both vertical and horizontal faces. Okay, now you consider the equilibrium of this wedge shaped element ABC. In this case, we'll be considering unit thickness perpendicular to the plane. Okay, understand? So, in this, what we are going to find the normal and shear stresses on an oblique plane, which is making an angle theta with major axis, that is x-axis. Okay, with x-axis with sigma x. Okay, so now before that we'll find the forces acting on AC and BC, faces AC and BC in horizontal and vertical directions. For example, on AC we have force due to sigma x, which is sigma x into area of AC, sigma x into AC, okay, which is horizontal, and force on AC in vertical direction, that will be the tangential or shear stress due to tau xy, will be equal to tau xy into AC. Here area is AC into 1. 1 is perpendicular dimension that we are assuming as 1 unit. Okay. Similarly, on face BC, we have vertical force due to sigma y, which is sigma y into BC into 1. Okay. Similarly, we have horizontal force on BC, which is nothing but the shear force on BC, which is tangential to BC. Okay, and what is that force equal to? Tau xy into BC area. Okay, so now if you replace these forces, acting on these faces, the stresses by forces P1, which is due to sigma x. Okay, so sigma x into AC, and P2 is vertical force acting on AC. So tau xy, that is the tangential stress into area AC. Similarly, P3, which is due to sigma y on BC. So what is P3? Sigma y into area. And P4, tangential force on BC, which is due to tau xy and is equal to tau xy into BC. Okay, that means here P4. Okay, now what we want is, what are the normal and tangential components of stress on inclined plane AB. Let us find the forces first. in normal direction and tangential direction. Okay. So the components of all these forces P1, P2, P3, P4 will be taken along the normal and tangent. Okay. Now, for example, this is angle theta, so this will be theta, and this will be theta, and this is 90 minus theta, for example. So, what are the forces acting in x direction? For example, here P1 towards left and P4 towards right. Okay, and in y direction, you have P2 upwards and P3 downwards. Okay. Now, what are the components of these forces in the direction of Pn and Pt? Okay. Now, let us see. Component of P1 will be P1 cos 90 minus theta along normal, and that of P4 is P4 cos 90 minus theta, that is sin theta. P1 sin theta and P4 sin theta. These are the components of forces, and one will be negative, one will be positive. And which one we have taken positive here? P1 we have taken positive. P1 cos 90 minus theta, that is P1 sin theta. And P4 cos 90 minus theta, that is P4 sin theta. Okay. And coming to the components of P2 and P3. P2 and P3. What are the components of this? P3 is towards the face AC, towards AC, and component of P2 is away. Okay. So P3 and P1 are of same sign. So we'll take what is the component of P3? P3 cos theta. P3 cos theta. This is theta angle. And P2 cos theta. They are opposite in direction. So with opposite sign we will take. So P3 and P1 are of same sign because they are in the same direction towards the plane. P2 and P4 are away from the plane. So P2 cos theta with negative sign and P3 cos theta with positive sign. Because we have taken P1 positive, so P3 also is positive components. They are in the same direction. Okay. Now you replace P1, P2, P3 and P4 by, in terms of stresses, we will substitute now. Okay. Sigma x AC. P1 is sigma x AC. Just now we have seen. P1 is sigma x AC. Similarly, P2 is tau xy AC. Okay. Tau xy AC. And P3 sigma y BC. P4 tau xy BC. Okay. So replace these P1, P2, P3 and P4 in terms of stresses. Now resolve these forces in the direction tangential to AB. This is the normal component Pn, tangential component Pt. What is it? So you have seen component of P1 along the normal is P1 sin theta. So along the tangent it will be P1 cos theta, isn't it? P1 cos theta. Directions are important. What is the direction of P1 cos theta? P1 cos theta is upwards, that we have taken positive. So P1 cos theta upwards, and direction of P2 is same as that of P1 in this case. Okay. Why? Let us see. Okay. P2 is also upwards. Its component is in the direction of P1 cos P1 component. Okay, which is upwards. P3 component is downwards and P4 component also is downwards. So they too are taken with negative sign. So P1 cos theta plus P2 sin theta minus P3 sin theta and P4 cos theta. So these are the components of forces along the tangent. Now we replace again P1, P2, P3 and P4 by sigma x AC, tau x y AC, sigma y BC and tau x y BC. Okay, as we have done here, we do the same thing here also. Now you find the normal stress sigma m as Pn by AB. Normal force divided by area of inclined plane AB into 1 will be the unit thickness. Okay. Similarly, tangential stress sigma t or tau, we generally take it as tau, which is Pt by AB. Tangential force, net tangential force divided by area. Okay. So what will you get? Sigma m. We substitute Pn, which is obtained as this divided by AB. Now splitting these terms, sigma x AC sin theta by AB. Similarly, tau xy into all these components, tau xy AC cos theta by AB and sigma y BC sin theta by AB, tau xy BC sin theta by AB. Okay, sigma y BC cos theta. This is sorry, cos theta. Okay, yeah, it should be cos theta, not sin theta. Sigma y BC cos theta. Okay. Now, what is AC by AB? Consider this diagram again. This is theta. So AC by AB is sin theta. Is it? AC by AB is sin theta. And BC by AB is cos theta. So what will you get here? Sigma x sin theta. AC by AB is again sin theta. So sin square theta. You will get sigma x sin square theta. Similarly, tau xy, it is sin theta into cos theta minus tau xy sin theta into cos theta plus sigma y BC is cos theta and we have already cos theta here. So sigma y cos square theta minus tau xy, this is cos theta into sin theta. Okay, so now rewriting this sin square theta as 1 minus cos 2 theta by 2. So we'll have sigma x by 2 into 1 minus cos 2 theta and this sigma y by 2 into 1 plus cos 2 theta, because cos square theta is 1 plus cos 2 theta by 2 and tau xy sin theta cos theta into 2. Okay, 2 tau xy sin theta cos theta, that is sin 2 theta. Tau xy sin 2 theta. Okay. Now we rearrange the terms here. Sigma x by 2 plus sigma y by 2. Sigma x plus sigma y by 2. Next, sigma x by 2 cos 2 theta minus, and here plus sigma y by 2 cos 2 theta. So taking minus sign here, you will have sigma x minus sigma y by 2 into cos 2 theta. So this is the expression for normal stress on an inclined plane. Normal stress on an inclined plane. Okay. Similarly, we will find shear stress. How will you get shear stress tau? Pt by AB. Tangential force PT by AB. Okay. So sigma x AC cos theta, PT value you have obtained already, that divided by AB here. Okay. So sigma x cos theta plus tau xy AC sin theta minus sigma y BC sin theta minus tau xy BC cos theta divided by A. Yeah, split them. You will have AC by AB sin theta. This is also sin theta. This is cos theta. This is cos theta. Okay. So sigma x sin theta cos theta plus tau xy sin square theta minus sigma y sin theta cos theta minus tau xy cos square theta. Okay. Now rearranging them, sigma x minus sigma y into sin theta cos theta plus tau xy by 2 into 1 minus cos 2 theta minus tau xy by 2 into 1 plus cos 2 theta. Okay. So what will you get here? Sigma x minus sigma y by 2 into sin 2 theta. What we are doing here? Multiplying and dividing by 2. So 2 sin theta cos theta is sin 2 theta. And here tau xy by 2 plus tau xy by 2 minus. They cancel. What will you have here? Minus tau xy cos 2 theta. And this is minus tau xy cos 2 theta by 2. Okay, tau xy by 2 cos 2 theta and tau xy by 2 cos 2 theta. So it becomes tau xy cos 2 theta. Okay, yeah. This gives the shear stress on an oblique plane under biaxial forces along with shear stress. Biaxial stresses along with shear stress. Okay. Biaxial stresses are sigma x and sigma y, and shear stress is tau xy. Under these stresses, the oblique plane will have a shear stress tau given by this expression. Okay, and now we can see the condition for maximum shear stress, also condition for zero shear stress. Zero shear stress means principal planes. Okay, so by equating this to 0, you will get the condition for principal plane. Okay, the plane on which the shear stresses are 0 called principal planes, isn't it? So equating shear stress to 0, you will have tan 2 theta P is equal to 2 tau xy by sigma x minus sigma. So we can represent this in the form of a triangle here. Tan 2 theta, okay, here is 2 tau xy minus 2 tau xy minus sigma x sigma y, and the hypotenuse is given as sum of the squares of these two sides, correct? Isn't it? Another case is plus sign. So here we can take minus as well as plus. Case 1 and case 2. With negative sign, we will take case 1. With positive sign, we will take case 2. So in case 1, what is sin 2 theta P? Sin 2 theta P1 is minus 2 tau xy divided by this. And cos 2 theta P1 is minus of this divided by this. Okay. Similarly in case 2, sin 2 theta P2 is 2 tau xy by hypotenuse. Okay. Yeah. These are the values. Okay. Now, principal stresses are found by substituting these values. Okay. Because this is the condition for zero shear stress. Means principal planes. Okay. In that case, sine 2 theta p, they are given like this. Okay. So substituting these values in the expression for normal stress, you will get maximum and minimum principal stresses. Okay. So for example, so here replacing cos 2 theta and sin 2 theta by these values, okay, this is one set and this is another set. Okay, so substituting these values, first the cos 2 theta p minus the, okay, so minus cos 2 theta is this and sin 2 theta is this. Okay, so what will you get here? This term will be as this, and here sigma x minus sigma y, minus of sigma x minus sigma y, and minus it becomes plus here. So sigma x minus sigma y square you will have, and in this term plus 2 tau xy square you will have. Okay, 2 tau xy square. So combining this also becomes plus, isn't it? Minus and minus becomes plus. So plus 2 you have, and here divided by 2, isn't it? So taking LCM and adding them, you will have 4 tau xy square, and in the denominator 2 into sigma x minus sigma y square plus 4 tau xy square under root. Okay, isn't it? Yeah. Here this is this becomes sigma x minus sigma y whole square plus 4 tau xy square under root, because this is same. Okay, this is just like x by root x, so it becomes the root x by 2 here, by 2. So taking this 2 into the square root, we will have sigma x minus sigma y by 2 square plus tau xy square. So this is the major principal stress or maximum principal stress. Okay. Similarly, substituting the second set of values, okay, into with positive sign, you will get another set. So here you will get negative sign. That's all. Okay. The remaining is as it is. You will get negative sign in this case. Okay. Yeah, you can observe here. Same thing you are getting. Sigma x plus minus sigma y square plus 4 tau xy square. Okay. Here this product is positive, so this negative sign remains as it is. Similarly, this is positive, negative sign remains as it is. Okay. Now taking negative sign common, here you will get positive sign. Understand? So the result is this, which is the minimum principal stress or minor principal stress, we call it. Okay. Yeah, for major principal stress, you will have positive sign. Okay. This is maximum or major principal stress. This is minimum or minor principal stress. Okay. So the condition for principal planes is obtained by equating shear stress to 0. Okay. That means you will get the theta values for which shear stress is 0. The planes on which shear stress is 0. Let us see one example, simple example. So a point is subjected to a tensile stress of 250 MPa megapascals in the horizontal direction, and another tensile stress of 100 MPa in vertical direction. Okay. The point is also subjected to a simple shear stress of 25 megapascals. 25 megapascals. So it is accompanied by shear stress here, complementary shear, such that when it is associated with the major principal stress, 25 megapascals is associated with major tensile stress. That is 250. So this is associated with major principal tensile stress. It tends to rotate the element in the clockwise direction. So the direction in which it tries to rotate is clockwise. So we have to take this way. What is the magnitude of the normal and shear stresses on a section inclined at an angle 20 degrees with the major tensile stress? So the section which is inclined at an angle theta with major principal stress, that is major tensile stress, is 20 degrees. Okay. So here what is asked to find the magnitude of normal and shear stress. So you can use directly the formula. For normal stress, we have formula sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau xy. So what is sigma x here? Major tensile stress, and sigma y is minor tensile stress, which is 100 minus 250 minus 100 by 2 cos 2 into 20 minus tau xy into psi 2 into 2 theta. Okay. So this comes out to be 175 minus 62.5 cos 40 minus 25 sin 40. So this comes out to be 101.48 megapascals. Okay. You can calculate. Similarly, shear stress is given as sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. So here also by substituting them, 250 minus 100 by 2 sin 40 minus 25 cos 40. This comes out to be 29.06 megapascals. Is this clear? We can take another example. Let us discuss this. A plane element in a boiler is subjected to tensile stresses of 400 MPa and 150 MPa at right angles. Each of the above stresses is accompanied by a shear stress of 100 MPa, such that when associated with minor tensile stress, tends to rotate the element in anti-clockwise direction. Find the principal stresses and their directions and maximum shear stress and the direction of the plane. Okay. So what does this mean? So let this be major tensile stress 400 MPa and minor tensile stress 150 MPa and the shear stress 100, such that when associated with minor stress it tends to rotate otherwise, okay, in anti-clockwise direction. The direction you have to take this one, and the other directions will be like this, okay, complementary. And what is the magnitude of this? 100 megapascals. Now, how to get maximum principal stress? So here sigma x is 400, sigma y is 150, and tau xy is 100. So the major principal stress, sigma p1, is obtained by substituting these values: 400 plus 150 by 2 plus square root of 400 minus 150 by 2 square plus 100 square. So this gives major principal stress as 435.1 megapascals. Similarly, the minor principal stress with the negative sign here, is it? For major stress we have positive sign, and for minor stress we will have negative sign. The same values, by substituting you will get its value as 114.9 megapascals. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.